Okay, so in this next example, we're going to take a look at writing a vector as a linear combination of a pair of vectors from geometry. So what we have here, in purple, we have a vector v1. In orange, we have a vector v2. And you can see a number of dots. And these dots represent the head of the vector. But we're leaving out the full line segment just to make sure that our page doesn't get too cluttered. Okay, but when you see the dot, that's going to be the head of our vector. So we want to write each of these vectors as a linear combination of the vectors v1 and v2. So let's take a look at this. If we look at the vector x, notice that this is the same length as v1, but it's pointed in the opposite direction. So for this example, I'll draw in the vector. So it's in the same direction as v1, just pointed in the opposite way. So this represents going backwards along v1. So we would write x is equal to negative v1. And if we wanted to write it as in terms of both v1 and v2, the numbers that we're going to see are negative 1 v1s and 0 v2s. Normally, we're just going to express it in this format. But you can see that there are coefficients for both v1 and v2 here, negative 1 and 0. Okay, next up, let's take a look at the vector a. So if we think about how we could get to vector a here, traveling only in the directions of v1 and v2, one way you might see us getting there is to go first the vector v1, and then at the end of vector v1, going along the vector v2, and then v2 again, and then v2 again. So we can write a as v1 plus 3 copies of v2. When we draw in the full vector, this is the diagonal of this triangle formed by v1 and the 3 copies of v2. Okay. All right, let's take a look at another one. Next, we're going to look at b. So we want to think about how we can arrive at b using the vectors v1 and v2. Now this time, we can imagine getting there by starting out at the origin. If we travel in the direction of v2, get v2, 1, 2, 3 copies of v2. Then we're going to go in the opposite direction of v1. So negative v1. We go negative v1 and negative v1. Okay. And so b can be expressed as negative 2v1 plus 3v2. The way that we wrote it, we first went in the direction v2 3 times, and then in the direction v1, in the direction of negative v1 twice. We could have also expressed this beginning by going to negative 2v1, and then traveling along 3v2, 3 times v2, this stretched version. And notice that we arrive at the same ending. So it doesn't matter whether we first travel in the direction v1 or in the direction v2. We'll arrive at the same landing spot. Okay, one last example. We're going to look at how we get to the vector c. Notice this time we have that c is partway along one of these curves, but what we're going along one of these lines. So we'll produce the best estimate that we can here. But if we think about traveling parallel to v1 and v2, trying to build to this spot, we can see if we go to, we're going to begin by going to 2v1, and then we're going to go in the direction opposite v2, and we want not a full length of v2, but instead half of v2. So this is going to be minus 1/2 v2. It's pointed in the opposite direction of v2, and it's only half as long. And there you have it. We have expressions for these vectors x, a, b, and c in terms of as linear combinations of the vectors v1 and v2. With this vector c, we see that that we can express vectors that are not on these grid points in terms of v1 and v2. And in fact, if we want to get to any vector that we like, let's choose one, maybe here, any point, any vector head that we like, we can arrive there by going some amount of v1 with then as well something in the direction parallel to v2. So even though here it's a little bit harder for us to see what these lengths are going to be equal to, we can still arrive at this endpoint using these directions v1 and v2.